I apologise. Right. So question 4 is quite a nasty one, and I think it's just by the wording. But again, you can just do the deduction thing. Okay, so for a body performing in simple harmonic motion, okay, so obviously you're going to have to be looking at simple harmonic motion equations for this. Which of the following statements is correct? A. The maximum kinetic energy is directly proportional to the frequency. Don't think so, but we'll go through each one in a minute. B. The time for one oscillation is directly proportional to the frequency. C. The speed at any instant is directly proportional to the displacement. D. The maximum acceleration is directly proportional to the amplitude. Now let's just think what happens in simple harmonic motion. So we have the simple, we have the basic principles, okay, which acceleration is proportional to the displacement. Okay, so in other words, it's maximum at the maximum displacement. In other words, it's maximum at the maximum amplitude. It's in the opposite direction to displacement. So if it's moving that way, the acceleration is going to be going that way. Okay, and obviously it's going to be so they're the two principles. But what we know, okay, the general facts of simple harmonic motion, it's got a greater speed at its equilibrium position. Okay, it's got its maximum acceleration at the maximum point, as we said. Okay, and obviously we've got equations to go with it, but they're the principles. Okay, and just using that, out of them you should see D is correct, but we'll just go through each one in turn. Okay, so if you just wanted to know, it's D, but we'll, as I say, I probably shouldn't mention that, but we'll go through it in each option, so if you didn't get that, don't worry. Okay, so again, let's have a look at let's just have a look at A. A says the maximum kinetic energy is directly proportional to the frequency. Okay, so therefore, if something's directly proportional to something else, so the kinetic energy is directly proportional to the to the frequency. Okay, the kinetic energy is directly proportional to the frequency. Well, therefore, it's saying the kinetic energy is equal to the frequency times a constant, and we label that constant K. Well, let's just think about what the kinetic energy is. Kinetic energy, for anything, okay, and you might read it as EK, or I read it as KE, it doesn't matter, is equal to a half of mv squared. Now, if we look at the velocity equation for a body in something in simple harmonic motion, it's equal to 2 pi f, or 2 pi over t, so it's plus or minus 2 pi f, or 2 pi over t, times the square root of a squared take x squared. Okay, now obviously you could put that in there. Obviously it's going to be the positive velocity that you take in this account because you're squaring it. Okay, so therefore you could put that in there and say, well, is the frequency times something to get kinetic energy? Well, it's not just times one thing, is it? It's times 2 pi, and then it's times the square root of a squared take x squared. Sorry. So therefore it's definitely not answer A. Okay. Now, for those of you who are just guessing, we've just chosen A twice, so therefore it's not likely to be A again. Okay, so it's not going to be A. I've tried to give it a best explanation as I could. B. The time for one oscillation is directly proportional to the frequency. Well, again, let's just have a look at the time equations we've got. Okay, so we've got two time equations, obviously depending on what it is. Okay, is it spring or is it a pendulum? And we need to consider both just to make sure we're not missing something out. Okay. But as I say, the answer is D for those of you that just want to get this over with. Okay. So just make sure the camera's still on. So the equation is 2 pi times the square root of L over G. Now that's for the pendulum. Okay. For the spring, okay, it's the time period is equal to 2 pi times the square root of m over k. Might be k over m, but anyway, I think it's m over k. I need to double check that. But either way, you can quite clearly see. Sorry, I'm sure that's right, but you might want to just double check that. That is m over k. But you're given that in the formula sheet, so I could have just looked. But where's the fun in that? Okay, so you can quite clearly see the principle for B says the time for one oscillation is directly proportional to the frequency. So we'd go with the same route we did for this. Okay, so if it says the time for one oscillation, in other words the time period t, is directly proportional to the frequency, okay, Well, therefore that says the frequency times a constant is equal to the time period. Well, neither of these have a frequency anywhere in them. Now you could go, well, you are correct. In other words, you could say that velocity is equal to plus or minus 2 pi over t times the square root of a squared take x squared, okay? But then again, this is not the frequency. Sorry, direct proportion. Yeah, it's not, okay? Although I guess you could say, using basic time and frequency equations, none of this really works that well. You could say the time period is equal to 1 over the frequency. If you were applying that method, then yeah, sure, it's proportional. But it sure as hell isn't directly proportional, it's inversely proportional. So the time period is equal to k times 1 over, sorry, it's k times 1 over f. Okay, so that's, you would say it's inversely proportional. Now, maybe I made a bit of a mess up here, but I'm not really. Either way, it's not proportional. It's inversely proportional, or these are the time equations you would more likely use if it was actually about some proportionality between time and something else in simple harmonic. You use these two. I wouldn't really use that, but as I say, you could say it's inversely proportional, or you could say it's not really proportional at all, because these two are time periods for something in simple harmonic motion. This is just a time period for a wave. Okay, so maybe I shouldn't have brought that up anyway. Either way, it is definitely not B. So sorry if I just ended up confusing you a bit more then towards the end. Okay, so that's B out of the way. C, the speed. This is why I think this question is quite difficult, because you can see we have to do a lot of working out. Now, as I say, I wouldn't do all that working out. I would just think that, or if you did need to know anything down, I would do it. As I say, it doesn't really matter. They're not going to check your working. Okay, you don't get any marks for it. Anyway, so C says the speed at any instant is directly proportional to the amplitude. So again, we need to do that kind of thing. So the speed, velocity is directly proportional to the amplitude. Sorry, is directly proportional to the displacement. Which I'll write as x. So therefore what we're saying is the velocity is the displacement times a constant. Okay, now the velocity, that's the velocity equation, got it on there. X here, well, it's quite clearly x is not times by something to get the velocity, it's square rooted and taken away and times by something else. It's definitely not this, okay? But you could also think logically about it. If something is directly proportional to something else, and this will help us understand why D is correct actually. If something is directly proportional to something else, when one increases, the other will. Okay? And obviously when one decreases, the other will decrease. Okay. So in other words, what it's saying for C is the speed. The further you get away, okay, from the equilibrium, which is what displacement is, the greater the speed will be. Well, we know that's not correct. It's inversely proportional, because if we think again, logically, rather than equations, but you need to consider both, okay, to make sure you're not missing anything out. What speed is actually? It's actually inversely proportional, because the maximum speed, or the maximum kinetic energy, occurs at the equilibrium position as the bob, or whatever it is, pendulum or spring, goes back through the equilibrium position, okay, we get a maximum speed. So quite clearly C is not right. So we've gone through all of them, and none of them seem right, so they're quite clearly, all our hopes are kind of pinned on D here, because we've not looked at the other, well, we've looked at the other ones and none of them seem right, so unless we've missed something else by logic or equation that we've not considered, which we haven't, then it's going to be D. But anyway, let's just check. The maximum acceleration is directly proportional to the amplitude. So this can either be proved through the equation, or it can be proved through just knowledge. Okay, the acceleration equation is equal to 2 pi f, or 2 pi over t, minus that, and it's all squared, times the displacement. Now again, if the acceleration is directly proportional to the displacement, then A is equal to the displacement x times a constant k, okay? So therefore, if we relate this equation to the acceleration equation, well, they've both got x in there, and this k constant is represented by this negative 2 pi f all squared. Okay, so that's why it's D. Okay, again, you can either use that or use knowledge. Now you know the acceleration is, because there's the maximum change of velocity at the maximum point, because we've gone from a fairly high speed, okay, to a speed suddenly in the other direction. So there's a huge change there of velocity, because we're taking a negative velocity to a positive, or whichever way you're looking at it, okay? So therefore, there's the biggest change of acceleration at the maximum point, okay? Now, it's not the biggest velocity at the maximum point, it's just the biggest change in velocity, in other words, the biggest acceleration. So therefore, as we say, when something is directly proportional to something else, when one increases, the other does. So what it's saying here is the greater the displacement, the greater the acceleration. Well, you can quite clearly see, just putting numbers into that equation or using logic, you can quite clearly see, for question 4, our answer is D. So hopefully that's kind of explained the next bit. Now the next bit I probably want to, I know I've said I'll try and avoid pausing the videos, but there's quite a few diagrams in this next bit for question 5, so I think I'll pause the video, draw the diagrams on, and we'll get back underway. Okay, so what I've done for you on the board there is drawn these 4 graphs excuse me, that you're given in question 5. Okay, so obviously you've got graph A, B, C and D. Now, as you can probably tell, I started off drawing each graph thinking I've got loads of room. I got to this graph and I thought I've got 2 more graphs to do, and I've got like a quarter of the board to do it. So I do apologise about the shoddiness of that graph, but I couldn't be bothered redrawing them, and I think they're good enough anyway to prove the point. Okay, so the question says, which one of the following graphs shows how acceleration varies with displacement? In other words, which graph is correct for an object in simple harmonic motion? Okay, and obviously x represents displacement and the vertical line represents acceleration. Remember, acceleration can be positive or negative, so that's why in some cases it goes below the line. Okay, so again we need to think, well, what happens with acceleration for a body in simple harmonic motion? Okay, now the first thing that enables us to counter straight away 2 of these graphs, okay, is that the acceleration is 0 at 0 displacement, okay? So therefore, in other words, it should cross the y-axis or the acceleration axis, where it should cross at the origin, okay? Or it should touch the origin at least, okay? So therefore, straight away we can cross out graph B and graph C, okay? So now we need something else to distinguish, well, is it A or is it D? Now, I think the only way to describe this is the fact that the rate of acceleration doesn't change, okay? Because remember, acceleration, the equation is minus brackets 2 pi f all squared times x. Now don't be put off and think, oh, it's an x squared graph because we've got this squared here, and you think, oh well, therefore it's going to be the first one. Well, no, it's not, because this squared, remember, 2 pi f just comes to be a number. If it was the other way around, so if that was just the power 1 and it was times x squared, then yes, it probably would be this one. But because the squared is over the 2 pi f, in other words, just a constant, okay, it wouldn't be this graph, okay? So therefore it has to be that one. Or a better explanation you could say is that there's no change in the rate of acceleration, so we need a graph that's linear, okay? It would also be D. Also, acceleration is a vector, okay, because it takes in magnitude and direction, just like velocity does. So therefore it can be negative, and when it's going the opposite way, it will be negative, and it does in simple harmonic motion, so therefore we need a graph that is negative as well, okay? That where you could say, well, bring it back graph B, but you can't bring back a graph once you've discounted it, so therefore it can't be A, it must be D. So all of that drawing just for a few seconds explanation. Okay, so that's question 5. Question 6 says a part. Okay, so this next question, question 6, is gives us a bit of information. Okay, so we're told that there's this object which weighs 5 times 10 to the minus 3 kilograms. It's got obviously it's in simple harmonic motion. It's got an amplitude of 0.15 meters. It does in 47 seconds. It has 50 oscillations, and it wants us to calculate the kinetic energy of this particle. It lists a few different answers. Now, there's no point in going through each answer like I normally would, because, well, for these calculation ones, you're going to get one of them, and if you don't, you've definitely got it wrong. So, again, these ones that are not really questions as such, they're just simply calculations, and they've got a list of answers. You've got to choose which one. And it's very helpful, but to be honest, it's easier just to ignore them answers and see what you get at the end. Okay, so there's no point in me going through is it A, B, whatever. Okay, so it asks us to work out the kinetic energy. So, well, the first thing we're going to need to do is, obviously we know the mass, so there's no point trying to work anything from that. We need to work out the velocity. Now, you know the velocity equation, V equals 2 pi over t, or 2 pi f, I'll put 2 pi over t, okay, times the square root of a squared take x squared. Now it's asking for the maximum kinetic energy, and you should know that occurs, the velocity is where the displacement is zero. Obviously, to give us the biggest velocity, you should use that equation, so therefore, obviously the displacement should be zero, in other words, x is zero. So anything we've got to work out, okay, is either the time period or the frequency, obviously, depending on which velocity equation you went with, if you went 2 pi over t or 2 pi f, okay. I'm going to work out the time period for you, okay, so therefore, so the time period is how long for one oscillation, okay. Actually, should I, let's check if I did it that way. Yeah, the time period for one oscillation. So in 47 seconds, there is 50 oscillations. Okay, we need to work the time for one oscillation. Okay, so divide both sides by 50. So therefore, one oscillation is 47 over 50. That's the time period. Okay, so 47 over 50 is equal to the time period. Now you should know 1 over the time period is equal to the frequency. So therefore, you could work from that. You could do the frequency. Okay, which is obviously 50 over 47. And whichever you chose, you subbed it into the velocity equation. So therefore, we get V equals 2 pi. Now, obviously, it depends whether you did over the time period. If you did it over the time period, you do 2 pi over this, over the time period. Okay, it's 2 pi over 47 over 50. In other words, 100 pi over 47 times the square root of a squared take x squared. Well, obviously, it's only going to be a squared, so you might as well just times it by a, because what you're going to end up doing is timesing it by 0.15. The square root of 0.15 squared, take 0 squared, square rooted. In other words, you're just working out times 0.15, but you need to you don't need to show that because there's no working marks, obviously. So again, that's what you're doing. Just sub their numbers into your calculator, and you should get an answer of 1.0026, etc. But it's not asking for the velocity, remember. Just for accuracy, I would leave that as a saved answer in your calculator. Okay, so now we've got the velocity. All you need to work out now is the kinetic energy, which is this kinetic energy equation as you would normally use it. Okay, so the kinetic energy is a half times the mass, which the mass is 5 times 10 to the minus 3 kilograms, times the velocity squared, which is 1.0026, etc., etc., all squared. Okay, so therefore you would just work that out. Okay, again, sub it into your calculator, should get an answer of 2.5 times 10 to the minus 3 joules. Okay, obviously when rounded, etc. And that is answer B. Okay, so therefore question 6, you'd pick B as your answer. There's no point trying to consider anything else because we worked it out. Absolutely nothing we've done wrong there. Just go back and check. Obviously, if you've not got this answer where you've got it from, then please do let me know if you've got any problems with calculating it or see what I did there. But hopefully it's very self-explanatory. It's nothing too difficult. Okay, for a simple harmonic motion question, they could have made that a lot worse. Okay, so anyway, that's the simple harmonic motion for question 6. So by quite a blast of simple harmonic motion questions, so I don't think there's that much more that you can ask. But, oh, yep, another question on simple harmonic motion. Okay, so question 6. Question 7. So question 7, is a simple pendulum, has a time period of 1.42 seconds on Earth. Okay, so I'll just put time period and then there's a little brackets, I'll put Earth. Okay, so time period on Earth we are told is 1.42 seconds. Okay, and on the moon, oh, we're not told on the moon, sorry. On Mars, where am I getting moon from? Mars' gravitational field strength is 0.37 times. Sorry, one sec. It's 0.737 times that of Earth. So, in other words, it's 0.37 times our gravitational field strength, which is 9.81 newtons per kilogram. Okay, so hopefully you see that. Right, so that's all the information we're told, and we're asked to use that information to work out time period at the pendulum on Mars. Now, if we didn't need this time period on Earth, because you may be going, why the hell is it telling us a time period on Earth, and then telling us Mars' gravitational field strength, and then ask the rest of the questions on Mars, but they've just told us the time period on Earth for some strange reason. Is there any way we can just, can we do 0.37 times the time period on Earth? Well no, okay. There must be a reason they've told you that time period, okay. Now, obviously, because it's mentioning time periods and we have to calculate a time period on Mars, it's given a time period on Earth, so we have to look at the time period equation. Now, obviously it's talking about a pendulum. Okay, so the time period with a K in it, it's not a pendulum, that's obviously for a spring. So the time period for a pendulum is 2 pi times the square root of L over G. Okay, so that's the time period for a pendulum. Now, if you look at that, okay, so it's just imagine if we just tried to calculate the time period for the pendulum on Mars. Okay, so obviously we know what we know what 2 pi is. It's a number. Okay, it gives it in your calculator. G, well, granted we don't know Mars' gravitational field strength, but we're told it's 0.37 times Earth's. Okay, so obviously you would put that equation in there. However, we don't know the length. But seeing as on Earth we're told the time period, we obviously know gravitational field strength, but we don't know the length. Okay, that's all we don't know. We can use the time period on Earth in the time period equation for a pendulum to enable us to work out the length of this pendulum, which we can then use to answer, because it's the same pendulum, okay, they're not changing the length, they're not that nasty, although probably in your exam they probably will be, they get worse every year. Anyway, so as I say, all we need to do is use the time period on Earth, and obviously all the gravitational field, so that goes with that, so L over 9.81. And rearrange that equation, times it out where necessary, so therefore you get what the length of the pendulum on Earth is. So obviously divide both sides by 2 pi, so 1.42 over 2 pi is equal to the square root of L over 9.81. Square both sides, okay, so 1.42 over 2 pi all squared is equal to L over 9.81 times both sides by 9.81. So therefore the length of the pendulum is 1.42 over 2 pi all squared times 9.81. Okay, and that should give you your length of your pendulum. And as before, because we've got to use that in another calculation to give us our end answer, whatever that gives you, okay, I think sort of gave me around 0.5 meters, okay, to round it, but as I say, you would leave whatever answer it gave you in your calculator and use it and save that as a length, but make sure you're not adding anything else to that answer. So, as I say, how competent you are with the calculator, if you think you're advanced enough to be able to save that and use it in a later equation without adding 2 to it by mistake, I've done that, so you can kind of guess that from me, why I keep saying use it as a saved answer, because I can't, so if it's going to screw everyone else up across the country, hopefully it should be alright for me. Anyway, no really, I mean, you should be hopefully confident enough to understand that. Okay, so now we've got the length, we know Mars' gravitational field strength, obviously 2 pi is a constant, so we can work out the time period on Mars, and hopefully it's one of the answers they've given us. So the time period is 2 pi times the square root of L over G. Now, L, as I say, we've worked it out as 0.5, etc, etc. And I would say leave that as you would save the answer you just worked out before, over 0.37 times 9.81, and that's because we've just been told that's Mars' gravitational field strength as of Earth's. In other words, it's we take Earth's gravitational field strength and times it by 0.37 and we get Mars. Okay, so therefore you work that out. Okay, so it's 2 pi times the square root 0.5, etc, etc, over 0.37 times 9.81. Shove that all into your calculator. You should get an answer of 2.33 seconds. Now, I rounded that up after I looked at the answers, obviously. Okay, so 2.33 seconds is there. It is. Sorry, it's option C. So for question 7, it's option C. And as I say, you had to kind of do 2 calculations, and for 1 mark, that's quite a lot of work, and I think you'll agree. So yeah, it's quite nasty. Right, so that's question 7 over and done with. Okay, now this next one, question 8, I can calculate, is quite a nasty one again. Now this is because, I don't think it's so nasty, but I did this paper as a mock quite recently, and because obviously we're doing it as a time pressure exam, trying to get into your exam mode and all, I found it quite wordy in the sense that I knew what it was asking and I could quite easily do it. Like when I did it on, just doing it at the side of my desk before, I could do it, I did it like that. But when I was sat in the exam mode, I was looking at the question, I was going, what the hell? Oh, actually no, sorry, it wasn't this question. Sorry, no, was it? Yeah, good. I've got 2 different questions, so look, half of the paper, one half over there, another half over there. Sorry, yeah, it was this question, and I just sat there looking, I go, what the hell is it asking? I mean, I know how to answer it, but I'm not getting